Now we'll focus on classifying matter by its components. So again, right, we're talking about chemistry, so we have to be able to kind of identify, well, what is chemistry, right? What is matter? And so matter is defined as kind of anything, right, that has substance, takes up space. And so now we want to get into, well, how do we classify matter? And this will help us, understand better, right, what we're talking about exactly. And so let's look at this. And we have this nice flow chart. And so the first question that this flow chart kind of presents is one type of particle. And so before we get into mixtures, let's kind of answer, well, what is a pure substance? Because that's a little easier to understand. And so now we have two options for pure substances. So pure substances could either be an element or a compound. And so the question is, what is an element? So an element is anything on the periodic table of elements. Use this. So I have one in the notes. We can also, let's see if I remember to pull it up. I did pull up my, I guess this is my current favorite online periodic table, ptable.com. So if you're ever unsure of a substance, right, check it here first. And so I'll make a point, for example, right, like gold is on the periodic table, silver, copper, zinc, but then I don't know if you all know this or not, right? Brass, nowhere to be found on there. So let's say you had no idea what brass was. First step, right? You at least look here so we can identify it is not an element. And so let's look at some other scenarios for elements that sometimes confuse students. And so let's just clarify here. So we said they had to be found on the periodic table. And the other key factor here is that they are going to be one type of element. And so what I mean by that is, well, let's go ahead and discuss allotropes. So what are allotropes? And let's start with carbon. And you probably know some carbon allotropes without even knowing it. In fact, you could be writing with one. And so let's switch over. And so I'll just say, right, Wikipedia is a great resource for science in general, a lot of standardized facts, but definitely use other resources for other things. All right, so looking at our allotropes, we'll start with our most basic ones. So this is just from our Wikipedia page. This is a good example. So not all inclusive of all allotropes, but basically, well, let's first define what the heck is an allotrope. You can kind of tell this from the picture, get an idea what an allotrope is. And let's just define it now. So it is defined as different geometrical arrangements of an atom. And so now if we go back to those pretty Wikipedia pictures, we can start to decipher them. So the first one here shown is diamond. So we notice diamond takes this repeating tetrahedral pattern. So carbon, then carbon at all these vertices. So that is what contributes to the strength of a diamond. So there's our diamond here. And so again, the other key thing with allotropes is, right, it has some sort of defined structure. So that is what all these names are referring to. And so if we go over to graphite, so now graphite, which that is going to be potentially what you're writing with right now. So notice pretty strong in the 2D structure, but then it has weak, essentially sheets. So weak intermolecular forces between these different layers. And so those layers then can shear off and allow you to write. And then the next one is Lonsdale Night, which I'm not really familiar with. D here is C60. So this was pretty famous. So discovered, I believe, back in the 90s. And so this kind of led to the whole explosion of carbon nanotubes. So this was a revolutionary material discovered at Rice University. And then from there, right, this led on to different nanotube structures with carbon. And then we get into, trying to scroll down. So G is just amorphous carbon. So basically, right, your pile of carbon. Amorphous meaning no structures. You can kind of tell that. And then H here is going to be your carbon nanotubes. So again, that extended from this area of research, and then this goes into carbon nanobots and blah, 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 blah. So there's a whole vein of research and materials all based off of nanotubes. And again, that being said, right, not all inclusive. And so let's look at other potential allotropes that, again, tend to maybe confuse people. So carbon, again, let's write down our examples. So diamond, graphite, I'll end under there C60/nanotubes. Just give us a general idea. And so other common allotropes, again, not an all-inclusive list, but just common ones that we might run into. So phosphorus is another famous one. And of course, most people have perhaps heard of white and red phosphorus. Of course, white is used in war and, military use, unfortunately. It is officially banned, but then it's still used actually to this day. That's how it goes. Anyways, we won't get into all that. We're just focusing on the chemistry. And so appreciating this little pyramidal structure of white phosphorus. And then we have red phosphorus, so formed from heating white phosphorus. And I believe they use it in matchsticks. Maybe. I was looking for the structure of red phosphorus. And then we also have violet phosphorus. And so again, at least appreciate that structure. So again, different 3D arrangement. So that's what we want to take away. Here's another one. So black phosphorus. So this is thermodynamically stable. And just appreciate it. Here's more top-down view. This gives us kind of the better 3D. And so, right, also diphosphorus. And so some of these are probably, and this mentions it, right, only obtained under extreme conditions. And so that's the other thing about chemistry. And often, I get a lot of questions in class of like, oh, has this been done or this been done? And really that's where you want to look at the literature, because that's kind of the fun part of chemists is chemists always want to make new bonds, new molecules, explore and push the frontiers. So, even though, again, we might not discuss a particular allotrope, we can see, well, P2 does exist, again, under extreme conditions. So, again, just that's where you would turn to the literature if you really wanted to know, hey, does, this exist? And feel free to email me, reach out to me. You can also comment on my YouTube if you're not one of my students, and I can always help you understand that. All right, the last allotrope we're going to cover is sulfur. And again, just because this is one of those that students are confused about and don't, it's funny. And it's what I mean is, well, if you see sulfur by itself, sometimes in a chemical reaction formula, it is listed as S8. And most students are confused about this. And yes, this means that we have a ring structure of sulfur. And so this is the most common allotrope of sulfur, is this funky 8-membered ring. So again, oftentimes, even if you're adding, let's just say, one equivalent of sulfur, you will have S8. And, maybe you'll have to put 1/8 of S8 to indicate, right, you only want one sulfur. But we'll get into balancing equations and all that later in these series of videos. But again, we're appreciating, so sulfur does exist as S8 in this ring structure. Again, people are not consistent about how they refer to it, so just keep that in mind. And again, right, many other allotropes. The key thing that we're looking for is that it's just one atom and different arrangements. So now let's look at, well, what is a compound? And so a compound is often defined as a defined or a known chemical formula. Let me get a smaller pen. And so I'll use a word defined. So defined chemical formula. And we'll look at some distinctions. And so we can start really simply. This could be CO, right? Carbon monoxide. We can go carbon dioxide. Water is a compound, right? Because it is a defined chemical formula. There it is shown above. Ammonia. And I'll add to this, right, 2 or more different atoms. And so they are different, right? So again, CO versus, oh, I knew I forgot something. Versus, I'm going to add under here, under allotropes, I should have added the diatomics. So the diatomics, let's highlight them on our periodic table. So again, these diatomics would be elements because they are one type of atom. And these diatomics, these just means that they are found in nature as 2. So again, similar to allotropes, except they are always found as H2. So H2 is the one odd one. And then the rest make what kind of looks like a 7 off to the side here. So I would go ahead and highlight this. If you don't have a printed periodic table at home, I would, do so. Even if it means, emailing me, I can print out some nice periodic tables on heavier cardstock for y'all. But come ask me if you need a printout. Otherwise, I would have, on your notes somewhere, maybe a dedicated periodic table or several versions, because as you'll kind of see as we go through this course, you want to annotate different things on our periodic table. And so now I'll write out our diatomics. Just so we have that, sorry. Show my pen. So our diatomics, again, there are 7 of them. So H2, N2 for nitrogen, oxygen, O2, chlorine, iodine, bromine. I'm missing one of them. Oh, fluorine. 7 diatomics. All right. So back to compounds. So again, we said they had to be 2 or more elements. That was the distinguishing factor. So we wrote ammonia, they can be larger molecules, right? We could get into, so caffeine, aspirin. And for some of these, you may not be familiar with the common name. On an exam, I'll try to give you, obviously, the formula. But let's kind of look at, again, some distinctions. So here is aspirin. And so the point that we want to make is we can look up aspirin, and it has a molecular structure here. And we can scroll down. Formula, right? Defined chemical formula. And so its formula is C9H8O4. We can switch to, I often joke that chemistry becomes drug the class. And here is, so cocaine. So again, right, a drug here. Here's the structure. And then defined chemical formula here. So C17H21NO4. And again, we'll dissect further what this means as we continue in our course. And so now let's kind of compare this. Okay, so we said this was a defined chemical formula. Well, what if it's more than one type of particle? What is a mixture? Let's look at some mixtures and what that means, and again, compare them. And so first of all, let's make this distinction before we get into kind of mixtures versus compounds. It asks us uniform throughout, and we have heterogeneous versus homogeneous. And I often say, well, is the first bite the same as the last? Kind of like homogeneous. And again, right, it should be, we can also properly define it as a uniform mixture. Versus heterogeneous, right, where it's not going to be uniform. And again, I'm thinking of chunky chocolate chip cookie dough ice cream, where you have, one bite is full of cookie dough and maybe the next is more ice cream. Here, we're showing kind of, if you were to scoop that sand right on the edge of the beach or even the water, and you have some of that sand at the bottom, you got water up top, and it's kind of settling and distinct layers, right? That is going to be heterogeneous. And so heterogeneous, it may be easier to think of some examples. I'll add again some classic ones like salad dressing. So it could be like the Italian one where it's immiscible and you have, 2 distinct layers, or maybe, even those Caesar dressings. They have different, I don't even know what's in there. Those little chunks, right? Basically, is it chunky or not? I'll add under there Swiss cheese, especially if it has holes. And, this is where some debates or confusion could occur. So if anything was ever confusing on an exam, right, write a note. Like, Swiss cheese, assuming it has holes, is heterogeneous, right? Because maybe your Swiss cheese just doesn't have holes. A better cheese is probably blue cheese, right? That's got weird veins and, extra mold on one part. Salads are heterogeneous mixtures. We'll do kind of rocks and sand, especially if it's, again, kind of like a pebbly beach where you get the rocks on top, sand on bottom. And so, what might be harder to make a distinction from, again, kind of depending on your familiarity, is going to be compounds versus homogeneous mixtures. And so, I want to point out, right, some examples and help you kind of think about what is in them. And so, we can start off with this example that's shown right here. So, tea with sugar. And so again, right, think about what makes it a mixture. So we have tea. Well, think about what chemicals are in there. Obviously, you boiled some water, and then maybe your tea has a little bit of caffeine. Even if it's green tea, it might have some caffeine. And then think about all that stuff that makes a tea. And generally, we kind of just call that tannins, but that is a big classification of molecules that essentially is responsible for everything, right? The flavor and giving us, again, other benefits to whatever tea. We could get into that some of these are related to like capsaicin. So like capsaicin obviously is the molecule responsible for spiciness. And so let's look at other mixtures. And so a tricky one is Alka-Seltzer. Let's spell that. And I'm especially looking at this like cold one. And so let's pull up the ingredients. And so I have here just the Alka-Seltzer plus severe cold and flu medicine. And so again, it could be confusing because if you look at it, if you've ever taken an Alka-Seltzer, and this is what makes it homogeneous, right? It's just a little tablet, a white tablet. So you might assume, right, it's just one thing. But we need to look at, well, what is in it? And this gets us really thinking about what are these different, things, medicines that I'm taking? What are they? Are they one thing? Are they mixtures? It's always good to research because, you should look it up. You may not know. And so if we're looking at this one, and so Alka-Seltzer Plus actually has aspirin in it. So we'd mentioned that, right, as a chemical. We can go back. There's aspirin. Oh, yep. Defined chemical formula. So that's our compound, or one compound. Then we have other ones. So dextromethorphan hydrobromide. So a cough suppressant. So we could look that up, right? That would be another distinct chemical. Then phenylnephrine bitartrate. So nasal congestion. So those are just the drugs, the chemicals. And then don't forget about what makes Alka-Seltzer fizz, right? So kind of think about, what does Alka-Seltzer do again? It dissolves, it gets bubbly. And that is because of these inactive ingredients, because, right, it's only going to refer to active as in drug, not just, reactive. And we have in there some citric acid. So that's going to be our acid. And then, so probably some other, maybe, what are they called? Preservatives in there. Notice red 40. But I'm looking for, we have potassium bicarbonate and sodium bicarbonate. So that is our base to mix with our acid. Once you dunk it in the water, it gets dissolved. Acid base reaction gives you a little fizzing. And then notice, right, sucralose in there. So also a compound. So a lot in that little, homogeneous looking pill. And then we can go back and understand, okay, that's why it's a homogeneous mixture, right? It's the same throughout. You could split the Alka-Seltzer if you wanted to just kind of dose yourself half, and that would be fine. It would still be your uniform mixture. And so we can think of other kind of common mixtures, any sort of soda like Coca-Cola, 7-Up, right? All those are going to have water, sugar, different flavorings, acid, phosphoric acid as preservative, etc. Different sugars. Gatorade on the homogeneous mixture train. And then we could do, right, vanilla ice cream, mayonnaise, especially right once it's freshly made. I understand, things can separate over time. We can probably think of other examples. Put shaving cream. Paints are usually homogeneous mixtures, right? They're not going to have weird chunks in them. And of course, right, feel free to think of your own examples, and you can always email or comment if you have questions.